groups starting up in that field to attain the full sensitivity. He's helped a great deal. He's also, of course, over the period of time, he's done a lot of spectroscopy. And then a few years ago, he measured the rotational spectrum, micro-rotational spectrum of cornene.
Quenulane.
Okay, I'm sorry.
C20H10. Thank you for the opportunity to speak here and for this nice introduction. I will actually not talk about quenulane today, even though I realized it would have fit perfectly. I was not aware that this is so heavily pH dominated. So the molecules I show are large and have carbon, but not that many pHs. And it will be, as you might guess now after this introduction, a little bit more like instrumental than the other talks. So this is the overview of it. First, for those that are not microwavers, show a little bit about the spectroscopy and what the strengths are, and that we really can exploit the narrow line shapes. Some of the instruments we have of the like classical type and more modern types, and maybe what we will build in the future if we ever get money. I tried 2 times and failed, I must admit. Very sad. But I'm continuing trying. I'll throw some example of complex organic molecules, and then what precise FT-MW spectroscopy might do for you, and how you might also be able to apply this to astronomy or astrophysics in a more fundamental way. So microwaves are characterized by, or the sources are characterized by high spectral purity, wide range of tunability. Microwave spectrometers go from like 0.3 gigahertz to 3 terahertz. Depends a little bit on the definition. If you, nowadays many people call that terahertz. If you're in infrared, you just call it far infrared. If you're microwave, you might call this submillimeter wave. It's maybe probably not that new as these terahertz people or T-ray people sometimes claim. Anyway, so we need polar molecules, and we can then look at molecular complexes, radicals, or stable molecules. In static gases or jets, we have high sensitivity in principle, even though the photon energy is not that large. So there are some disadvantage compared to infrared or certainly visible or UV spectroscopy from the energy of the photon. But we tend to have quiet detectors, and we regain a lot of the characteristics of our detectors. We can see that therefore isotopomers in natural abundance in many cases determine molecular structure. We have high resolution. We can resolve fine, hyperfine structure of the rotational lines and use these splittings to determine intermolecular dynamics or from the spin rotational coupling electronic structure in the molecule. So this is basically the instrument we have. It's a big spherical chamber with a large diffusion pump that enables us to operate a repetition rate of 20 hertz. It's an emission technique or coherence technique, schematically described like this. We first introduce a molecular jet in our chamber. Molecules, after supersonic jet expansion, rotate in an incoherent fashion. Then we introduce a short microwave pulse. We treat this as an ensemble, not as individual molecules, so a more appropriate way to describe this quantum mechanically is to use a density matrix rather than a single particle wave function. And this is how the density matrix looks like. The diagonal terms are the population terms. The off-diagonal terms are the coherence terms in principle, or basically this gives the population of the level A and level B in the beginning. Before we have coherence, these off-diagonal moments are 0, and after you applied the microwave pulse and created coherence, as we see in the next slide, these become non-zero. As a result, these molecules are now rotate with, in this fashion. The individual dipoles don't cancel out anymore. You get a macroscopic oscillating dipole moment that create a macroscopic electric field in the resonator that you can calculate using Maxwell's equation, and you can couple this out of the resonator. You get, of course, the advantage of the resonator Q enhancing your signal. Get this FRD, looks just like an NMR spectroscopy, Fourier transform this and get your spectrum. And by applying this coaxially to along your resonator axis rather than doing this perpendicular, you get very good overlap between the active region of the resonator and the transient of your molecules. And that enables you to get very, very narrow line widths that then give you very, very sharp peaks. This is our machine, a big chamber here. You see Helmholtz coils here, so we can also look at radical species without having to worry too much about the Earth's magnetic field. This is one of our mirrors. This was in the beginning was already just constructed to look for larger molecules that have small B values, so the spectrum has a tendency to be shifted to low frequency. So the resonator is slightly bigger than what you might normally know from Fourier transform machines. It's about 63 centimeter diameter. About the same distance between the mirror allows us to operate down to 2 gigahertz. We have here in the center the hole for our jet nozzle, and then 4 more holes here, 2 closer, 2 farther away from the center, for 2 pairs of antennas, one antenna to polarize the molecules, the other one to pick up the molecular signal, and we use one pair for the upper part of the frequency range of our spectrometer, the other one where the antenna is also a little bit longer for the lower part of the frequency range of our spectrometer. We can use lots of sources to create more exotic species that you can't buy from Aldrich, and that might be also created in the interstellar medium or violent areas of the universe. We can do this with laser plasma. We can do this with electric discharge, with laser photolysis, pyrolysis. We can also mix molecules in the nozzle, get chemical reaction, and look for intermediates that survive supersonic expansion before they react to something else. We can look at non-volatile species using laser ablation. And all of this, we can use all this to look for molecules that can be radicals, ions, or neutral species that are important in combustion, atmospheric chemistry, astrochemistry. And we can determine the structure if we can look for fine and hyperfine interaction. And we can also, that's something more new for fundamental topics in physics that I might, if I have time, show in the last few slides. This is a complicated slide. I apologize for this. Basically describes the normal Fourier transform microwave experiment where you do a so-called pi over 2 pulse. Basically, this blue vector here, the Bloch vector, is aligned with this W axis in the beginning. Projection to the V and the U direction is 0. That basically describes the beginning of the experiment where you have no coherence. These are a linear combination of the coherence terms of the density matrix, and this is then the population difference. And then you flip this by 90 degrees into this plane. So you equilibrate your population and completely converted your population difference into coherence, and then it rotates in this plane if you don't have relaxation. You do this with the pulse that is resonant or near resonant to your molecules. You basically describe a very, very narrow region of the spectrum where you hopefully have a transition between the level A and level B. Instrument look like this. Again, don't look at all these components. I just color-coded here the RF part. Basically what happens is you have a synthesizer and a microwave. Use all this to polarize your molecules in the microwave region. This block here in this color is the detection part. You pick up your microwave signal in your molecular signal in the microwave region, then it's down converted into the radio frequency region. You don't historically had to do this because of the speed of the A to D converters and to limit the amount of data you have to store and Fourier transform. And especially because your resonator is narrow banded, it doesn't make a lot of sense to convert your signal directly in the microwave range of 30 gigahertz, but the usable widths of your spectrum is only megahertz. You can convert this down and then store it coad and then do the Fourier transform. What I only want to show you is that's quite a lot of components that you need, and you might just remember the number of components. Which is basically all in here. There's lots of cables. Most of these cables are actually used. So what done new, we saw briefly something yesterday in a talk of the Harvard group, is that instead of doing fixed frequency pulse, you do a chirp. And the difference in this Bloch vector picture of the chirp between the pulse and the chirp is this omega vector, which at fixed frequency would just be aligned the u-axis and stay there and just be on or off when you have your pulse on or off. In this picture, you just flip this vector from being very off-resonant to some transition, which means aligned to the w-axis 180 degree to the opposite direction. So it's very off-resonant to the center frequency in the other frequency direction. And in all this way, if the lines resonant, you just polarize those lines. So you just, instead of having a Fourier transform limited pulse, which is a very, very limited spectral bandwidth, you just are able to polarize many, many lines. And as you see here, if you do this smart with the correct power and the correct length of this chirp, you can also flip this blue vector, which in the beginning was aligned to the w-axis, into this UV plane, which means optimum polarization. So you can get exactly the same molecular excitation for a given transition as you can get for the traditional pi/2 pulse method if you do it correctly. The disadvantage, of course, is because you're broadband, you can't have a high Q resonator anymore. So you have to use a setup without a resonator, so you lose the passive amplification that you have with a resonator. On the other hand, you save a lot of time, so you don't have to step in very, very narrow steps anymore through the spectrum, because you get a gigahertz or several gigahertz in one shot. You can use that time to integrate more single experiments. And for molecules in high abundance with a large dipole, in the end you gain. Setup is like this. Same color code I used here. What you might realize is that the number of components are just much, much smaller. To build a spectrometer like this, with the broadband electronic components like arbitrary wavefront generators, high bandwidth scopes nowadays, you need a very, very limited amount of microwave components here, because a lot of conversion steps you don't need. So the spectrometer is much, much simpler, except that unfortunately some of these components are much, much more expensive now, so you don't save money. On the other hand, my prediction is that if you look at synthesizers, they don't become cheaper. All this analog technology, phase lock loop oscillators, they just don't become cheaper. Whereas everything that has to do with digital electronics becomes faster and cheaper very quickly. So my prediction is that these spectrometers will be very cheap at some point. Maybe you can't buy classical synthesizers anymore in a few years. It's all be done by digital analog conversion. So this is a traditional setup where you have two horns, no resonator here, and then you can use several nozzles in between those two horns and expand your molecular species between those horns. The disadvantage is, because of the transit time, your line width becomes large again, so compared to the coaxial resonator experiment. So it's a very fast experiment for broad frequency reasons, but you lose resolution, which might hurt you if you need it. This is the first setup we did, not in Hannover actually, because the Violith people had money first. So now the amount of electronics, if you remember the other picture, is just very, very limited. No moving parts, you don't have to tune the resonator, that's another advantage. And the first spectrum we actually did was an alkaloid nicotine. In this setup you get a gigahertz in one shot, and in about 10 minutes you get a spectrum like this. That's a gigahertz broad. And there were actually two conformers in this molecule, which are easily identified. The fit is very easy because the lines are narrow, not as narrow as in the resonator experiment, but still narrow enough so that you don't have a lot of problems with blending, even though you have many lines or many conformers. But I show an even more complicated example later. You can combine this with laser ablation also. One setup would be doing it like this, using instead of 2 horns, 1 horn, and then a reflector, and use the same horn to irradiate your molecules and also to pick up the molecular signal. This actually was one resonator mirror that was just there in the lab. But you do not form a resonator here, because then you couldn't make, or at least it might have like a small Q, but nothing that limits the bandwidth too much. And what we could see here doing laser ablation was vitamin C, again a 1 gigahertz spectrum. 3 different rotamers, which are all present here in this spectrum, and 9,000 cycles. This spectrum was taken. And
was I seeing sort of a whole series of rotational transitions?
yeah, that was a whole series of rotational transitions. These are all different rotational transitions. And then these symbols here tell you to which rotamer they have been assigned. So these are kind of low J rotational, pure rotational transitions.
Roughly what J? I'm just curious.
I think that was maybe like 5 or 6, below 10. A problem here with vitamin C is there are lots of possibilities of intermolecular hydrogen bonds and of many conformers. These are the ones that have energies below 700 centimeter to -1 of, and the result of the study basically was that they do networks of hydrogen bonded similar cooperative networks, and we show better example in a few slides. And 3 of them have been determined by comparing the experimental results with the ab initio rotational constants that we calculated for many of the species that were possible candidates. So, and that can be easily done because of the resolution, and because of, even though there are many possibilities, in the end you only see 3 conformers, and that's not so difficult to disentangle. And the other thing also was, that's important here, is with laser ablation, show better example, or even a better example later, is that your laser doesn't destroy the molecule. We tried this with heating, also sugars, also this. We tried this with different lasers. And as I show in a moment with the sugars, is that really using a picosecond laser rather than a nanosecond laser helps you a lot in avoiding decomposition of your sample, to the extent that that you might not get any decomposition products at all, whereas in the past it was a big problem. What we then did is, instead of using this 2-horn setup or horn reflector setup, we use this setup, which is actually looks like 2 TV dishes, except that they charge us a lot of money compared to what you normally pay if you buy it for your home television. So what we do, you have basically a reflector horn antenna setup facing each other, and what happens is, or what the idea was, and which worked quite well, is you have a horn here, you do your microwave pulse, which expands, then the reflector makes a parallel beam out of that, and then the second reflector focuses it, because it's symmetric, to where this horn was before. We removed the second horn and put a flat plate here with a nozzle setup, or laser ablation nozzle setup, that we also use in the resonator. And the idea is you need a lot of power for these broadband methods. And but what you really need is not power. You need field strength to polarize your molecules, get a pi/2 pulse equivalent to that. So the idea was to focus this first diverging beam to where you have the highest particle density, so you can maybe live with a cheaper, smaller amplifier, still get the field you need to get the perfect polarization. Now it turned out with a 1 watt amplifier, which we first thought might be enough, you still don't get a full polarization of like a normal dipole species. You still need somewhat more, like a turn wave 2 amplifier. Probably it's not, you can't avoid, but still you might do with 10 watts or 100 watts rather than several hundred watts. And the other thing is, even though this is not a resonator like the Fabry Rotap resonator, this is just basically a dual pass. You go through here, then it's reflected, goes back, it's dual pass, it's not a resonator, so this doesn't limit your bandwidths by some Q. So you still can make a broadband experiment, several gigahertz, and you gain this advantage of focusing the power, and you gain the advantage of having a similar situation as in the resonator by shooting kind of coaxially to your field. So compared to the setup where you have two horns and the nozzles above the horns, you have a longer interaction time, a longer transit time of the molecules, after the molecules radiate. You have a lot more time to pick up the molecular signals. You get a narrow line again after Fourier transform with the longer signal. And this is actually spectrum of difluorophenol, where again you get this Doppler doublet like in a resonator, but again you get these narrow lines like in a cavity of less than 5 kilohertz. So you again, what many people now will do, use a broadband machine, approximately look where the lines is. If you have nitrogen, you can't resolve it. Then you know the line position, go back to the resonator machine, measure the same line at higher resolution. You don't have to do this anymore. Because mostly the resolution is sufficient to resolve all the lines completely. With a cavity machine, you still get a line that about like maybe 80%, a factor of 2 narrower, but you're almost there. So another thing, large carbon molecule as C5 sugars. It's something started with Frank Lower some years ago with, when he asked us to look for ribose. I'll tell the story a little bit later how this developed. Ribose looks like this, C5 sugar, and of course it's in the RNA. Whether that has anything to do with life, if you find it in space, I don't know, but maybe not. But it's an interesting molecule. The question is, what is the structure, and can we resolve the spectrum? Can we assign it? And actually, this ribose, even though it's a small sugar, has a lot of conformational freedom. You can get a pyranose, a furanose, you get a 5-ring or 6-ring. And then these OH can be in beta position or an alpha position. So overall, you get 8 different structures, fundamental structures, plus the open chain. But it does not stop here. Then also, all these OH groups can form intermolecular hydrogen bonds, networks of bonds, and and then they're all different. So you get a myriad of local conformational minima, and you basically have to calculate them all to figure out what are the low energy species. So this is how it actually started. We did ribose first. First try was 2006. We used IR laser ablation. There was an IR laser, nanosecond laser, 8 nanosecond pulse lengths. And we got a rich spectrum with lots of molecules, except we couldn't assign it. I mean, we couldn't assign those, but we couldn't assign ribose because you get all kinds of crap. In the end, later, like when we were successful, we also saw that we had 13 transitions belonging to ribose, but at that time we just couldn't assign them because of all these other lines, which were just decomposition products of the molecule. Because it very easily eliminates water, and you get secondary reactions. And then we stopped this project for some time. Still, I started to work again on this with the group in Bilbao. This Emilio Cochinero and Alberto Lesari. They had a picosecond UV laser just purchased. We set up the microwave machine there. There was a laser group before which didn't have microwaves before. And this laser basically made the difference. We basically got no decomposition products, as I'll show in a second. But we started with doing this quantum chemical predictions of all kinds of different conformations and pyranose rings, furanose rings, linear forms. Pyronos are the lowest in energy, furnos a little bit higher, and the linear forms are even higher, so we expected pyronos. But we didn't get where it would stop here. Problem, of course, is microwave really powerful enough to identify very, very rich spectra with very, very many conformations? I mean, normally, yes, we know this, but how far can we go? And we are quite, especially if you have many, many different conformers that all only differ very little in B. It's not like having 2 or 3 different conformers with very different A, B, and C. They're all very similar. They're different but similar. So, but before we looked at this molecule, which is an anesthetic, and that was actually an interesting spectrum. You look at this, you see a number of lines. I mean, for microwave, that's a lot of lines. I mean, I made some paper. I made more than one paper that had less than 10 lines. I mean, infrared people maybe are not impressed, but for us, that's a lot of lines, because you can zoom in here, and you see more lines. I mean, in a microwave spectrum, and you zoom in a microwave spectrum, and you see more lines. But we can assign every single line with 100% certainty, more or less, because most of them are really unblended. And once you have your fit running, we really know like this fit worked, and so you can identify those lines, even if it's very, very dense, as we expected in Ribose. So this is a 1 gigahertz, no, actually 2 gigahertz again. We did with Ribose. It was a conventional again with a COBRA machine, with a resonator machine, and we found 6 conformers that were positively identified, but no decomposition products, which we had mostly before, that prevented the assignment in 2006. And of course, identification goes the usual way of your experimental A, B, and C. You compare them with ab initio calculations. Sometimes, if A, B, and C is not that, it's a little bit ambitious, you can also look at the dipole moment component. Sometimes A, B, and C are very similar for 2 conformers, but the dipole moments differ. So we look at A, B, and C transitions, how they behave when you change the power, and use this as an additional source of information. And then finally we assign these 6, which then correspond to these cooperative hydrogen bond networks, which are counterclockwise or clockwise. These all are pyrene rings. And we have 3 beta forms here, and 3 alpha forms. And the structure steering, of course, is depends on the topology of the ring, so how close the H's and O's can come, and also stereoelectronic contribution, so-called anomeric effect, which basically, as a simple picture, tries to minimize the dipole moment of the molecule. From the relative intensities, we can also try to get relative energies and compare them to the calculated relative energies from the ab initio calculations, which doesn't work that well here, because it works well if you don't have rotational, if you don't have relaxation, but we have considerable relaxation here in the jet, so that's why the match is not that good. But at least those conformations that have been calculated as the lower energy ones are also the ones we found in the jet. And then, of course, I mean, this is for slightly different audiences slide here, but the idea is to, of course, look for larger species in the interstellar medium compared to glycolaldehyde and dihydroxyacetone that already have been identified as being in space by Frank Lovers. And I'm not at the end of my talk. I hope I could convince you that microwave spectroscopy is a powerful method. I mean, microwaves already know, but hopefully others, that even larger molecules, complex molecules that have a conformational variety can be easily identified in microwave, and then especially with now more sensitive telescopes that exist now, you can identify those in the interstellar medium probably lots, much more there now. It's just a matter of sensitivity to find them and sell it. The next few slides are not carbon molecules, but it's I will switch back to carbon molecules at the very end of my talk, showing you that other things that we do might also be applicable to things that are of astrophysical interest. I want to start with this slide showing our resolution, which is 10 to minus 7 centimeter to minus 1. I don't give this number in kilohertz anymore, because if you're an audience of there are not many microwavers there, you give it in kilohertz, nobody is impressed because nobody knows what that number means. But if you give it in centimeter to minus 1, you typically get a better response. And so that's the resolution we have. And for unblended lines, you can determine the center frequency of a transition to an order of magnitude more, maybe even more if you really push it hard. If you integrate long to get a better signal-to-noise ratio, or the best signal-to-noise ratio, again, you can go to maybe down to 20 hertz if you really want to. For systems where really you know what it's doing, you don't have anything on the baseline, and you have strong signals. So, and we can exploit this resolution, for example, to look at very subtle, tiny effects like Born-Oppenheimer breakdown. I just show you this. As an example, you get Born-Oppenheimer breakdown, especially when you get electronic states that are close together so they can interact. So normally if you have a single sigma state, nothing happens. You get these so-called Born-Oppenheimer breakdown coefficients that are on the order of unity. Here for tellurium selenide, you have triplet sigma state with closely lying electronic states that interact. So you get large effect, large Born-Oppenheimer breakdown contribution that are for both atoms, tellurium and selenium, about the same size. Or here for lead selenide, which is a single sigma state, you wouldn't expect this because there are no electronic states that would interact, but you still see a large Born-Oppenheimer breakdown coefficient here formally for the lead, not for the selenium. And the reason here is that lead is such a big atom that you can't treat it as a point mass anymore. It has a volume, it's not a point charge, and which then results in a Born-Oppenheimer breakdown coefficient that we can determine to quite some accuracy. Anyway, that's just why we like how we started and realized how good this resolution is for small effects. One thing that people are looking at lately is, or actually quite some time, was the dipole moment of the electron, which the standard model predicts to be really, really tiny, so there's no chance of ever measuring it. But there are other models that predict a larger dipole moment for the electrons, so-called supersymmetry models, that require more parity violation than the standard model allows for, and one already knows that there are additional sources because to explain the imbalance between matter and antimatter and other things. So that we need something in addition to the standard model. And even though this is a very, very tiny value, there are actually experimental method where you can set a lower limit on this order of magnitude here. And if you do be a little bit better, you can eliminate some of those. And except that if you make it small and you eliminate one of these theories, they can be reparameterized and then they magically reappear here. So that's kind of fun. Anyway, what I want to show you really is that you can, if you have a dipole moment of the electron, then the M states, which we all know are degenerate, the states that have just different in the sign. However, if the electron does have a dipole moment, then these M states would have a small energy difference, and you could detect this in a strong E field that is alternately parallel or antiparallel to a B field, and from this, and you can then determine from this energy difference the electron, the dipole moment of the electron, if you know the effective field that the electron sees. The major difficulties here is, which might actually in the end, our advantage is that this measurement is poisoned by background magnetic fields. So you have to really take care of stray fields and have that under control. Otherwise, it would mimic a false electron-electric dipole moment. So you have to be really, really careful with your setup. We first tried lead fluoride in a collaboration with Niels Schaffer-Ray, which is radical, and we can create this molecule doing laser ablation, just using our neodymium laser, ablate elementary lead. Then we have SF6 in our gas, in the laser plasma. Also, this SF6, 1% in neon typically disintegrates, reacts with the lead. It's expanded in our resonator. We can see those molecules and get narrow lines. And we can also, by turning off our Zeeman coils to Zeeman spectroscopy, depending on which coils we turn off, parallel or perpendicular to our microwave field, we get different selection rules and can then determine the molecular G effect of that molecule. Now, we have not measured the electric dipole moment of the electron in these species yet, because there we need to still improve our experiment quite a lot. However, this was done on this molecule using LIF or Rampey methods, and then we put it in the microwave machine, and within a few days, actually, we could improve everything by 5 orders of magnitude. That's a good start. Bad news is there's still some orders of magnitude to go, but we are down here now. And actually, there's also some parity violation effect, just only 1 order of magnitude away, which we might see in the near future with the so-called nuclear anapole moment. Which basically you probe. You have the nucleus, and you have to have some helical currents in your nucleus that are parity violating, and that has also an effect on your hyperfine structure and magnetic field. But of course, since this has something to do with the nucleus, you want to have something that's electron density where near the nucleus. So PBF might not be the best molecule because there's a pi state. So you looking at something which is in a sigma state, which, for example, is the terbium fluoride that we recently measured and are still measuring. Has also an unpaired electron, but in a sigma state. And we're hoping to see this anapole moment, or at least get a better upper limit value. What we could do now is just improve together with some other transitions out of some other spectroscopies and other frequency regions, get a global fit and get a number of these parameters to very, very high accuracy that then also helps in determine the value of these moments, because you can compare these values with ab initio calculations and then verify how good they can predict effective internal fields that then are used in the calculation of the electron-electric dipole moment. Anyway, but now we come back to the topic of this conference or this workshop. What you do is you have 2 M states and look at them, and if the electron has a dipole moment, they're slightly different energies. So if you want to look at this way, they rotate in a slightly different angular rate. So if they would be exactly degenerate, and one rotates in this direction, the other one rotates in this direction, you would maintain a polarization, the direction of your linear polarized light. And one of these M states rotates slightly slower, or the other one slightly faster. Then with that energy difference or frequency difference, the direction of the polarization direction rotates. And you can detect this much, much better than trying to get a tiny splitting for a line that is broader than the splitting than you expect, because the splitting we expect are in the like hertz range or millihertz range. So what you do is you do a spectrometer. This time I didn't color code this. You just need more components, but you have as main difference, two detection antennas here in 45-degree to your polarization antenna. So you look at your molecular signal. You have the same amplitude at the beginning of your experiment after you do the polarization, and if then the amplitude rises here and decreases here, that means the polarization direction rotates, and from that rotation frequency, you can determine the energy difference between of the two states. And the idea, of course, now for us, for example, is, since we might actually never see the EADM, use this parasitic effect that we had to be very careful there to eliminate, to use this as a very sensitive Zeeman spectroscopy method for molecule, also for closed shell molecules where you normally need large magnetic fields. So you see an effect compared to radicals. So we want what we don't want here. We might be able to use in the future for doing Zeeman spectroscopy. For example, for a molecule like this, which is methanol. Methanol is used also in an astrophysical context as one of these candidate molecules where you can see variation of the proton-electron mass ratio over the years. And what you do is you look at certain A and E states, internal rotation states of methanol in the lab, and from sources that are far away. So the light is like millions or billions of years old, and you look for difference. And what we did last year actually is somebody asked me, like, how can you measure these lines to a precision less than a kilohertz? I said, okay, of course, yes. But then I looked at these lines and it's just full of hyperfine structure. And even though there are other papers which are probably correct, but I still have a hard time believing that they're as correct as they claim, error-wise. Of course, if you measure a line at a high signal noise ratio, you can determine the center frequency to a fraction of the line width if you think you know the line width, the line shape. But I don't think we know the line shape of this one here, because this hyperfine structure is not under control. So one of, and it's also not that resolved that we can easily fit the hyperfine Hamiltonian to this line. So what we're still about are to improve our resolution, to get like a real quantum mechanic fit to assigned components of this. Hyperfine structures in the presence of large amplitude motion is not that, it's not like it's a rigid molecule with a hyperfine structure, so the Hamiltonian is different and the line positions are affected, so that's hard. So Laurent Coder is working on this with us. And the other thing is the line shape also affected by a Zeeman effect? This is measured with our Zeeman coils on, so this is probably not Zeeman splitting, it's all just hyperfine. But if you turn them off, there might be some little changes here which are hard to detect because of all these other hyperfine components. So the line just may broaden a little bit. But using this, the other scheme, and looking at the change of the polarization direction rotating with the frequency that corresponds to the frequency difference of the different M states that you get that are not degenerate after you have an external magnetic field, and then determine the molecular G factors that way. Or if you look in space, and I think the methanol, some other molecules, similar effects have been observed, but then there's some magnetic fields are claimed, or the size of the magnetic field is claimed. It's not obvious to me on which basis. So maybe that also helps to get a hold of magnetic fields in certain parts of the inter or circumstellar medium. And this is second to last slide. And the other thing you can also do if you have two antennas looking at different polarization direction that are different from the excitation direction, use this the microwave in a double resonance scheme to determine the absolute chirality of molecules. There's a paper here that recently came out where this was demonstrated. using a Stark effect actually, but you can also do this in a pi over 2 pi scheme, doing double quantum coherence. And with this, I want to close this talk, and the people that collaborated, the agencies that gave money, and I'd like to thank you for your attention, and hope that you're even more convinced now than you might have been before that complex organic molecules, also all this weed you might see now at higher frequency region, or you can tackle with microwave, because also of this high resolution, even the centimeter wave range, that helps in determine centrifugal distortion constants that you need to extrapolate spectra that have been measured in the lab in centimeter wave region, but with less accurate method might not help much to then determine line positions in the millimeter or submillimeter wave. Still, of course, good to combine this with higher frequency method in a global fit, but precision always helps. Thank you.
So we have actually a little time for questions. We have to vacate by 11:30. David?
Yeah, so you said you got something like 3 to 4 orders of magnitude more to getting sort of a detectable, or to get to where EDM measurements are currently sort of have their current upper limit?
Yes. So to reach this, you have to do many things.
Yeah, I guess I'm just wondering, I mean, you pulled many tricks out of your hat.
Yeah, I mean, to do 1 order of magnitude is probably not that high. You can slow down the molecules using a heavier carrier gas. You can cool it down. You can use a Stark decelerator. You can also change the geometry of your resonator so that the expansion of the jet contributes less to your line widths. I forgot to tell you that most of the line shape we have, basically everything of the line shape, is instrumental. The line shape we have is basically determined by the instrument. So, and you can change a lot, or you can change the instrument or the setup, the geometry of the resonator, the transit time, and get a narrow line.
So, I mean, you know, the conventional tricks that people have used, I guess you're not, is using some external field to be able to then have the molecules more or less polarized in the laboratory frame, and then the strong electric fields in the molecule as a measure of EDM. Is there any way in which you can?
Well, you need a small external field to create an effective internal field in the molecule. This started with atoms. This is
sure.
I'm happy to answer this question, but maybe it's. People started with atoms, and you need a ridiculously high fields to get internal fields. And with molecules, where you have states of opposite parity close lying with rather small external fields, you can get internal fields on the order of up to 100 gigavolt per centimeter.
I'm sorry, maybe I missed that. Are you actually having some laboratory field that is then mixing?
Yeah, we then, what we can also do is we have our resonator, which is insulated, and then we can apply a Stark field between those resonator plates, and we have ways to make it very homogeneous. And
you're using that now.
We use that now for more or less conventional Stark spectroscopy.
I guess what I'm saying is using then some sort of laboratory-based field, is that part of your factor of 10 to the 4 improvement that you're going to get?
It also contributes to it in the way you have to find the right molecular system. You have to, of course, have this field under control because it shifts your Stark lines. So you have to have this field under control to a precision that is guarantees that your line stays there better than you have to determine the frequency. which means you have to determine this. You have to have a Stark field and control to an accuracy of like 4 orders of magnitude. If you do this with kilovolts per centimeter, you're having a hard time reaching the precisions. For PBF, you need about 100 volts per centimeter. And 100 volts per centimeter, that's a reasonable number. But also, if you do a jet and you have a resonator that's, let's say, maybe a meter long, you have to multiply 100 volts per centimeter by 100. So then again at 10,000 volts, and then you have to control this to that accuracy. And then already, again, you probably are unable to do this. Yeah, but there are other molecules which I didn't show here. Where I should have shown tungsten carbide actually, because it has a carbon. Tungsten carbide is a triple delta 1 state, which has systematic degeneracy between states of different parity. And there you need a volt, and they're very close line because it's systematically. In the PBF, it's accidental. You have fine components that are sort of close together, give you that value. For the tungsten carbide, which has other problems, but for the tungsten carbide, you have systematically very close lying lambda doublets. And there you need a volt per centimeter. Then if you have a resonator that is a meter long, you need 100 volts. You need to control this accurately. And controlling 100 volts accurately is much easier than doing this with 10,000 volts. And of course, also if you have a higher voltage, need this voltage, you have parasitic currents that then might create parasitic magnetic fields, and you have to suppress them. So this is a hard experiment. And also there are competitors that are much stronger and much larger groups than we are. So, but it's fun. And you can always learn there to that's what I wanted to show here. Decreasing the line widths or using these methods, using the rotation of the rotation frequency of polarizing field, you can use for something else that might be applicable to other fields, not fundamental physics, just astronomy or astrophysics. Just exploiting or abusing what we learned there for to answer other questions.
Here's a question on the broadband experiments. One of the issues, of course, you get this tremendous bandwidth. And
Yeah.
In the case of Ribose, you get multiple conformers simultaneously.
Yeah.
The question then becomes this more generalized issue of complex mixture analysis and how you rapidly pick out these various conformers. And do you, in that case, did you use any
You mean like automatic
or anything?
automatic assignment method?
Correct. Yeah.
No, we didn't do this yet. But that's probably the way in the future. I mean, there's some pros. David Pasquale did some automatic assignment. Then Leo Mertz or Michael Schmidt, he did this very successfully. And there are different schemes using genetic algorithms or just trying and just use the speed of the computers. You just can't.
For the brute force.
You just I mean, you can do it smart, but also brute force might be faster than a human being.
You said yesterday, right? Why? Yeah. Don't.
Let's send a man to do a machine's job.
Exactly.
You're right. But the problem, of course, is you need the right Hamiltonian for this. I mean, if you
No, I don't think you do.
well, I mean,
I
if
think
you
you just need to. Well, I don't know.
well, if you have just a normal molecule with internal rotation, I mean, with centrifugal distortion. But if you look for molecules that have large amplitude motion and splittings, I mean, if you want to assign this, you need to know the Hamiltonian, the correct one.
Well, initially, but my thought is that you do, like they do in NMR, right? You do these multi-resonant, double resonance, and you can.
Oh yeah, so you mean
potentially
okay, yeah.
You can disentangle many
So
molecules.
of course, there are other methods to at least know which
Correct.
transition belongs to which species without
Correct.
a quantum chemical assignment.
Yeah. And
A quantum mechanical assignment, that's true.
Yeah.
And there are also other things that are called, I think, maximum entropy method, where we record the same spectrum at different conditions, different pressures, different temperatures. to record the spectrum like 10 times, and then there are algorithms that I have correlation Stone McNaughton doing this, that claim that you do this and it figures out for you which line belongs to which species and how many species you have in your spectrum. And it worked. I mean, so far we did this with known mixtures, and they kind of work. But known mixtures are different from unknown mixtures.
I was going to ask, like you showed that you could produce these sort of very fragile molecules very well with this ultra-fast pulsed UV light.
Yeah.
I've seen this several times now, but do you have any idea what's going on? Like, I would have thought naively that would be a disaster. Like, ultra-high intensities UV photons would destroy everything. Yet it seems to be the opposite.
Yeah.
Like,
Well, I mean, basically, that's what. When I started this, I just bought the cheapest laser I could buy. I was just like boil this thing off. So you got the cheapest IR nanosecond or 8 nanosecond pulse laser. But apparently that's not the case. Apparently, if you do it very short, then the molecule doesn't have time to. I mean, I don't know. To me, it's black magic, in a sense.
Do you find-
But it just.
is it sensitive to your target? I mean, I would have thought that the light would penetrate
I
many...
mean, one thing I didn't say this compared to our IR pulse. If you start with a UV pulse, which is still a multi-photon process, I guess, but you need less photons than with the IR if you start with IR photons, and you tend to need much less power with a UV laser than the power you need with the IR laser, just to get the probability of this multi-photon process, which is not linear.
So maybe it's
with
just
the power.
thermal. You're just
So
not-
maybe it's just thermal.
Yes, so you have at least two cases that you talked about where you jet cool and there might have been 20 potential conformers and you find 3 or 5,
Yeah.
something like that. Is there a way, I mean, can we learn from this something that allows us to be able to anticipate maybe under some other related system, just what conformers might be formed? In other words, are these conformers that are all, at the bottom of some, I mean, are these all separated by very large barriers?
Yeah.
Are
What
these
you
all
learn, you
relatively
learn. Yeah.
close in conformer space? I mean, is there some way that we can sort of learn something that's extracted?
Yeah, I mean, obviously, only those survive that have a sufficiently high barrier. If there's, sometimes we see molecules that have quite a high energy, and then there's another conformer which we don't see at all, which is lower in energy because there's just a lower barrier to the lowest one, so it just relaxes. And then what we can also do is we can change the carrier gas. So if you use neon or helium, you see much more conformers than with argon. With argon, in many cases, you only see the lowest one, or just very few, because the argon, heavier collisional gas is just able to kick the molecule over much higher barriers than the neon and helium is able to do so.
You may also be chaperone.
Yeah.
You may actually be generating a van der Waals complex that dissociates or gets removed in some other way.
Yeah.
You also have this comparison between first principles theory and what you actually really saw based on experimentally you extracted this by some sort of temperature analysis, I forget, but you had some presumption.
Yeah, basically you can of course look at the relative intensities,
Okay.
and you of course have to calculate the dipole transition moment,
So
and then you can calculate energies assuming you have no relaxation.
Right, but you were comparing that with theory, and I guess I would say that level of theory probably does not include zero-point effects, right?
Well, it's a correct zero-point effect, and we also start with delta G at room temperature, which seems to be important. If you have
So you think theory is corrected at a level that is...
if you have no relaxation, in many cases it works quite well.
So you think the differences between theory and experiment there were really, what, you're blaming,
I'm blaming relaxation.
you're blaming experiment.
I'm blaming the experiment. Yeah, it's very sad.
That's rather, okay. I would think that there's a lot of possible problems with theory at that level of precision for that large a molecule.
Well, we could also blame, of course, theory. You can say like you need a better theory that can take into account the barriers and then calculate different intensities. Because it's just a very, very crude approach to say like we have, what do we get if we have no relaxation?
So did you make any announcements this afternoon or something? I think, are there any more questions? I think we might. Thank you.
Good.